So here we start our final section, final chapter on reactions of carbonyls. And this gets into a class of reactions known as condensation reactions. Now, what we're going to see in this chapter are a series of reactions that are between two different carbonyl compounds. And in every one of these reactions, one of the carbonyls is our nucleophile, as an enolate, and the other carbonyl compound serves as our electrophile, as we've seen so many times before. Now, all that being said, two things come up in this chapter. First, there's really not a lot that's new in this chapter. Pretty much every mechanistic step that we'll see in this chapter is something that we've seen in a different reaction. We're just going to see them in a different way. Second, these are some fairly long, complex mechanisms, so keep that in mind as we go through them. The first one that we start with in this chapter is known as the Aldol condensation. The Aldol condensation, interestingly, is the only one of these condensation reactions that we're going to learn that's not named after the person who first discovered it. Now, this one, part of that is because this was discovered by two separate chemists working independently. And so we have Alexander Borodin, who first discovered this in 1869. You may also be familiar with him from a different context. He was an organic chemist, and that was his main work. But he was also a classical music composer and published wrote a number of symphonies, among quite a bit of other work. And then we also have Charles Adolf Wurtz, who published a very similar reaction 3 years later. So what is the Aldol condensation? So in sort of the simplest context, if you recall, in the alpha substitution chapter, we said we don't really use aldehydes very much for those types of reactions. And we said that the reason for that is aldehydes are often just too good as electrophiles to use in that type of reaction. And here's our reason why. So if we have an aldehyde and we add base to it, especially if we keep it cold and then quench with acid, our two molecules of the aldehyde will combine to give us this product. And it's actually this product that gives the aldol its name, because you can see that we have an aldehyde and an alcohol. And so in the name aldol, the Al refers to the aldehyde, and the ol, of course, to the alcohol. Now, in many cases with this reaction, especially if you let it get warmer, the reaction won't stop there, and that OH group will get eliminated to give you an alkene. All right, so how does this reaction work? Well, you can do this reaction under acidic or basic conditions, but in most cases, it's almost always done under basic conditions. We're not going to talk about the acidic conditions in this class. As we talked about in the previous chapter, those reactions are much less common because of the much weaker nucleophile under acidic conditions. Recall that meant that we had to use the enol and not the enolate. So in this sort of very simple case, we start with our aldehyde, and our base can remove the alpha hydrogen. That enolate that we formed can then do nucleophilic attack onto another molecule of the aldehyde. And we form this new carbon-carbon bond that I've drawn in green. From here, that O- will pick up a proton to give us our aldol product. But as we said, in most cases the reaction's not done. And the reason the reaction's not done is if it goes all the way to the alkene, this is a much more stable product. And so as long as we have enough heat for getting there, then we're going to go all the way to the alkene. So how does this occur? Well, we see clearly we get an elimination because the OH group is gone and we have an alkene. But it turns out this is not one of the previous elimination mechanisms that we've learned. You remember we previously learned E1 and E2, and then I may have mentioned that there was this third elimination mechanism, E1cb, that we would see at some point in the future. Well, that's what's happening here. So the E1cb mechanism is a two-step elimination, where in the first step, base comes in, removes the alpha hydrogen, and we form a new enolate. From there, that enolate adds in its electrons, the pi electrons shift over, and we kick out the leaving group. And that gives us our product. So as we can see here, we have a very new mechanism, we have a new mechanism, a new reaction, the Aldol condensation. But it's largely taken from pieces that we've already learned. Our first step this is just enolate formation. Our second step is a 1,2 addition. The only thing that's different from the 1,2 additions that we've learned before is that in this 1,2 addition, the nucleophile is an enolate. Here we just have a protonation. Obviously, we've seen many protonations before. We then have another enolate formation. And then, we finish our E1cb mechanism. So the only step that's really new at all is this last step. And again, we want to emphasize this is an E1cb mechanism. It's not an E1, it's not an E2, but it is an E1cb, which is a third mechanism for elimination. All right, so this is our first example, and maybe not the most exciting of examples, because in this example, we use the same carbonyl as our nucleophile and as our electrophile. And if that was the case for every one of these, that would be very limiting in what you could do with an aldol condensation. So most of the time when we look at aldols, we look at what we call mixed aldols. And by a mixed aldol, we mean an aldol where we use two different carbonyls. So one carbonyl is our nucleophile, one carbonyl is our electrophile. There is one major problem with mixed aldols. What's the issue? Well, let's say we tried to do this aldol. So what's wrong here? Basically, the issue that we have to deal with is now we've got two different carbonyls. Both of them have alpha hydrogens. So which one of these carbonyls will function as the nucleophile? Which one will function as the electrophile? And basically the issue is that either one could be. So we could have this one as our nucleophile, and this is our electrophile. Which would give us that product. We could have acetone react with itself and be both the nucleophile and the electrophile. We could have acetophenone, which is our other carbonyl here, be both the nucleophile and the electrophile. Giving us a third product. And finally, we could have acetophenone as the nucleophile and acetone as the electrophile. And so as you can see that we have four possible products from this situation. And this isn't as bad as it gets. What if our carbonyls had, multiple possible enolates? Then there's even more possible products. So how do we avoid this problem? How do we get it so that we only get, one product? So there's a number of different ways to do that. Probably the most common is to choose one carbonyl that has no alpha hydrogens. A good example of that is something like benzaldehyde. With benzaldehyde, there's no carbon on the right side, and the carbon on the left has no hydrogens. So benzaldehyde cannot form enolates. And since benzaldehyde cannot form an enolate, it has to be the electrophile. It cannot be the nucleophile for the reaction. So that's probably the most common way that we get around the problem. The second way that we do it is using ketones versus aldehydes. We know that due to sterics and electronics, that aldehydes are better electrophiles. And so in a lot of cases, if you have one ketone and one aldehyde, you can get the system to prefer the aldehyde as the electrophile, makes the ketone your nucleophile, and you get control that way. The third option is to rely on pKa differences. A lot of ketones and aldehydes are going to have very similar pKa's, but there are going to also be situations where the acidity is very, very different. Let's say we had a carbonyl like this, and we wanted it to react with this one, this dicarbonyl. Well, the key here is the carbonyl on the left has a pKa for its alpha hydrogens of about 18. Acidic, but not nearly as acidic as the one between the two carbonyls, which has a pK of about 8. And so if we choose the proper base for this reaction, then only the stronger acid will be able to be deprotonated. The final things we want to say about the aldol is the aldol is an equilibrium. So under the right conditions, you actually can get the aldol to go all the way back to the starting materials. It's not terribly common, but it can occur. And there are actually some other nucleophiles that you can use in an aldol. Again, less common, so I'm just going to mention them briefly. But you can use nitriles, and the enolate that you form here can attack, and also nitroalkanes. Because again, just like with the carbonyl or the nitrile, you have that pi bond that can stabilize the alpha carbon if you deprotonate it. Again, not terribly common reactions, but reactions that we can do, and these can be used as nucleophiles in an aldol condensation. So the aldol condensation is basically a 1,2 addition to a carbonyl. But if you remember back to the chapter when we studied 1,2 additions, we always had to account for what could compete with them, and that was 1,4 addition. So we'll pick up in the next video with what happens if our carbonyl that's serving as the electrophile, what happens if it's conjugated.